Here is a guided problem solving related to our topic, superposition cycle. Consider a cogeneration plant where steam enters the turbine at 7 megapascal and 500 degrees Celsius. So as you can see here, it enters the turbine at 7 megapascal and 500 degrees Celsius. So we can see that 1, 2, and 3 are the same state. So this is the entrance to the turbine. Some steam is extracted from the turbine at 500 kPa for process heating. So as you can see from the turbine, so meaning it enters the turbine and it is extracted for the process heating. So it is at 0.5. So we extract here some steam for the process heating at 500 kilopascal. Steam, the remaining is expanded to 5 kPa. As you can see, the remaining steam is expanded to 5 kPa to enter the condenser. Steam is condensed here at the condenser pressure, and after that it is pumped to the pressure of the boiler, which is 7 megapascal. So it's 7 megapascal after leaving the pump from the condenser. At times of high demand for process heat, some steam leaving the boiler is throttled to 500 kPa and is routed to the process heater. So this is where we can actually adjust the quantity of the steam that we use for the process heater. Here, some quantity of steam are extracted at 500 kPa. So using the valve here. So that's why we have 0.2 to 4. So the extraction are adjusted so that the steam leaves the process heater as saturated liquid at 500 kPa. So it leaves at 0.7 at a saturated liquid at the same pressure. So as you can see here, in order for them to enter the process heater, 5 and 4 have the same pressure. They are 500 kPa. So the mass flow rate, it is subcooled. It is subsequently pumped. So the one that leaves the process heater is pumped also to 7 megapascal. But since they are different fluid, they have to be mixed. So the hot fluid, the steam, and then the cooler one is mixed here before entering the boiler. So the mass flow rate of steam, the boiler is 15 kilogram per second. It refers to M11, M1, and it is 15 kilogram per second. So we are to determine the maximum rate at which process heat can be supplied, the power produced, and the utilization factor when no process heat is applied, the rate of process heat supplied when 10% of the steam is extracted before it enters the turbine, and 70% of the steam is extracted from the turbine at 500 kPa for process heating. So this is the equivalent TS diagram. So as you can see, 0.1, 2, and 3 they are the same state because they are all from the exit of the boiler entering here. So 1, 2, and 3 are 7 megapascal and 500 degrees Celsius. So 2 to 4 is expansion to 0.4 used at constant enthalpy. So expansion is actually constant enthalpy. So 3 to 4, while 2, 5, and 6, so it's expansion here at 5 and 6. That's why 3, 5, and 6 are isentropic expansion. And the rest of the cycle are also shown here in the TS diagram. So we are to fill in the table using the software or steam table. So at point 1, that is actually superheated vapor at 7,000 kPa and 500 degrees Celsius. Again, 1, 2, and 3 are the same points, both here and here. So we can get the value immediately from the software. And since 4 is this one here, this process 2 to 4, this is an expansion valve. So when we have expansion valve, that is actually a throttling process. And throttling is an isenthalpic process, meaning 2 and 4 has the same enthalpy. That's why enthalpy at point 4 is the same with point 3, and that is 3411.4. And using that value, we can get the entropy and temperature at 0.4. And then at 0.5, so 0.5 and 6 have the same entropy at 2. This is because this is an expansion here at 5 and 6. They are leaving the turbine, so they are expanding from 0.3. So they have the same entropy also. And since we have two properties here, then we can get the remaining properties. At 0.7, since it's saturated liquid and we're given with pressure, we can get the properties also. The 0.7, which is the one leaving the process heater, that is saturated liquid based on the problem. And then at 0.8, that is actually saturated liquid also leaving the condenser at 0.8 at 5 kPa. So we can get that immediately. 8 to 9 is pumping, so that's why they have the same entropy, and we can get the remaining properties. At 0.10, it's pumping also from 7 to 10. So 7 and 10 have the same entropy. So if 7 is 1.8068604, then 10 is also 1.8604. And since we have two values, then we can get also the temperature and enthalpy at 0.10. And at 0.11, we can leave it blank, but we will use energy balance here to get the enthalpy at 0.11 later on. So that's how you analyze to get the enthalpies of the steam. So first, we need to determine the heat supplied by the boiler. So we take the heat supplied as if there is no process heater. So the heat supplied by the boiler, assuming that there is the total heat supplied by the boiler is assuming that there is no process heater, meaning this portion here does not exist. So it will just go to a simple Rankine cycle, as you can see. So meaning there's no mixing chamber also, there's no pump here, pump to process heater, in order to get the total heat that can be actually supplied by the boiler without the process heater. And we can get that using the formula M1 H1 minus H9. We use H9 because we don't have mixing chamber anymore, meaning what you pump here at 0.10, it will automatically enter the boiler. And mass 1 is the mass flow rate in the boiler, which is also given in the problem, which is 15 kilogram per second. So using Q in, so the heat entering the boiler is just the difference of the enthalpy. So our Q in is actually 48,999.45 kilowatt. So this is the maximum heat that the boiler can supply. That is 48,999.45 kilowatt. So again, that is assuming that there's no process heater. Next is to determine the maximum rate at which process heat can be supplied. So meaning there's no turbine, but all the energy will go to the process heater. So for us to have a maximum rate in the process heater, we will not use steam for the turbine. We will use all the steam for the process heater, meaning this part here does not exist. So only the boiler, the process heater, and then the pump. So the maximum rate of heat of process heat is achieved when all the steam leaving the boiler is throttled and sent to the process heater, and none is sent to the turbine. And that is equals to M1 multiplied by H4 minus H7, because 0.5 does not exist anymore because we don't have turbine. So meaning it will just be one line. We have 0.4 entering and 0.7 leaving the process heater. So that's why QP max is 41,569.65 kilowatt. So assuming that all the energy will go to the process heater and there's no turbine work. Next, we determine the power produced and the utilization factor when no process heat is supplied. So when no process heat is supplied, all the energy from the boiler will go to the turbine, meaning this part here doesn't exist. So the process heater, the pump 2, the expansion valve, and the mixing chamber won't exist. It will just be point 1, and then we have point 3, point 6, point 8, and point 9. It's a simple Rankine cycle if there is no process heat supplied. So that we are going to determine the power that will be produced by the turbine when there is no process heater, as well as the utilization factor, which is also equivalent to the thermal efficiency when there is no process heater. So maximum power is produced in this process when there is no process heat supplied. All the steam will pass through the turbine and expands to the condenser pressure of 5 kPa. So our work net is just equals to the work of the turbine, or the power that will be produced is work of the turbine minus work of the pump. For the power produced, it just equals to the work of the turbine, which is M1, H3 minus H6, or the change of enthalpy in the turbine, minus work of the pump, which is M1, and the difference of enthalpy in the pump, H9 minus H8. So that's why our work net, when there's no process heater, if we substitute the mass flow rate of 15 kilogram per second, is 19,970.7 kilowatt. So this is the power that can be produced when no process heat is supplied. And for the utilization factor, that is just equals to work net plus Q pump over Q in. Since there is not Q pump but the process heat, so since there's no process heat, that's why it's 0. So it will just be work net over Q in. So as you can see, it's just like thermal efficiency. So our utilization factor is 40.75%. So meaning only 40.75% of the energy produced by the boiler is being utilized. The rest are expelled or wasted. Letter D. The rate of process heat supply when 10% of the steam is extracted before it enters the turbine and 70% is extracted from the turbine at 500 kilopascal for process heating. So what we mean here is that 10% will flow here, 70% will is extracted from the turbine. So meaning out of the 100% that flows from the boiler, 10% will expanded here, will be extracted here before it enters the turbine, and then 70% will be extracted here at 0.5 after expanding in the turbine. So the 70% will be flowing at 0.5, and the remaining around 20% will go to the condenser. So that's what this means here. So using energy balance at the process heater, using those values, our energy entering are 4 and 5, and the energy leaving is 7. So we have M4H4 plus M5H5 is equals to M7H7. Another energy leaving is the process heat. So take note that this heat will be used by the industry. That's the process heat. So it's actually a heat output, or heat going out of, or energy going out. So it's energy out. So the process heat is just equals to this value if we rearrange the energies. And using the mass balance at the process heater, the mass that enters are 4 and 5, and the mass that leaves is 7. That's why it's M4 plus M5 is equals to M7. Using the percentage from the given, we know that M1 from the given, the mass that flows here is 15 kilogram per second at 0.1. And then at M4, it is said that 10% of that is extracted here. So therefore, at 0.2 and 4, they have the same masses because there's no branching here. So that is just 10% or 0.1 of M1. So that's why we have 0.1 of M1 is M4. On the other hand, M5 is 70% based on the problem of the steam. So it's 0.7 of M1. And therefore, the mass that lives here is the mass of 4 and 5, right? Because energy in, masses in is equals to masses out. So that's just point M1, M4 plus M5, which is this one. That's our M7. So substituting these masses in the QP equation, where in M7 is 0.8 M1, we add this one. Our QP will reduce to this one. So 0.1 M1, 0.7 M1, and then we have minus 0.8 M1. And then substituting our mass M1, which is 15, and the enthalpy is 4, 5, and 7 from that we already got a while ago. So the process heat or the rate of process heat supply is 26,198.67 kilowatts. So this is the amount of heat that we can utilize for process heat. So when 10% of this with the same condition, we're going to determine the utilization factor. But before we can do that, we need to determine first the enthalpy at 11, because this time we already have a complete setup. So we have a process heater and a turbine. Because of that, we need a mixing chamber, and therefore we need to get 0.11 because it's still unknown here. So we have to do energy balance at the mixing chamber. So energy in and energy out. So we have 9 and 10, energy in and energy out is 11. So our M11 by energy and by mass balance analysis also is just equals to M1, right? And then we know that M10 is equals to M7 because there's no branching here. So the same mass flow here. So M10 is equals to M7, which is 0.8 M1. M9 on the other hand is equals to M8, which is equals to M5. And we know that it's, if this is 10%, this is 70%, and the remaining will just flow here, which is 20. So that's why it's 0.2 M1 at 0.9. So plugging in the value here, and then solving for H11, our H11 is just equals to 546.698. So as you can see, it should be between 9 and 10. So it's not greater than 10 and it's not lesser than 9. So now that we have H11, we can calculate now the by energy balance also of the entire system. We can determine the work net plus QP. So of the entire system, if we're going to do energy balance, the energy entering are the Q in the boiler plus the work of the pump and the work of pump 1 and 2. That's what we have here. Energy in and the energy out are turbine because it's producing work, plus the process heat because it's giving heat also away, and the condenser because it's rejecting heat. So that those are Q out. So if you rearrange that to solve for work net plus QP, we can see that if we rearrange it, our Q in minus QC is equals to work turbine minus work of the pump plus QP. Since this work turbine minus work pump is equals to work net, then we can reduce this equation to this one. So Q in minus QC is equals to work net plus QP. So our work net plus QP, which we need for the utilization factor, is just equals to Q in minus QC. Our Q in is equals to M1 H11 minus H1, or the heat input in the boiler, minus QC, or the heat rejection in the condenser, which is M6 H6 minus H8. So if we substitute the value, so our work net is just work net plus QP is 37,164.78. So our Q in for the entire system again is just equals to mass flow rate in the boiler times the change of enthalpy in the boiler. And that is 42,970.53 kilowatt. And now we can get the utilization factor. So the utilization factor is just this one. And since we already have work net plus QP and Qin, we just substitute those values to get the utilization factor as 86.5%. So as you can see, the utilization factor has increased from 41.18% when we don't use process heater, and it increases to 86.5% when we use process heater. So meaning we utilize 87% of the energy instead of rejecting those energy to the as waste heat. So that is how we analyze cogeneration cycle.